How old is the universe? This is a fundamental question in cosmology. The standard model of cosmology claims to have finalized the answer to this question, at approximately 13.8 billion years. However, increasingly, doubt is being cast upon this estimate because the James Webb Space Telescope is consistently pushing the galactic observational boundary closer and closer towards the Big Bang. This means that, quite literally, galaxies are being observed which seem to have formed far too quickly after the Big Bang. Each galaxy contains billions of stars, and according to the standard model of cosmology, many of the stars formed almost simultaneously with their host galaxy. This jokingly infers that the universe as we see it might have been hatched from some sort of cosmic egg, already fully formed, but young. The standard model of cosmology insists that some galaxies formed, with billions of stars, within a few 100 million years after the Big Bang. However, geological processes on Earth are often longer than this, so the standard model of cosmology position simply doesn't pass the smell test. Clearly, there appears to be a collision between the standard model of cosmology and common sense. In this episode, we dispel the myth of a cosmic chicken laying a cosmic egg, by computing a value of cosmological age, 900 million years older than the standard model of cosmology estimate, thereby allowing substantially more time for the galactic creation process. We predict that, in the fullness of time, the James Webb Space Telescope will confirm, directly or indirectly, that the correct cosmological age equals the Hubble age, that is, 14.57 billion years. Let's begin the journey by conceptualizing the universe. The standard model of cosmology conceptualization of the universe appears on screen. It's intuitive, simple and very easy to comprehend, however, it is profoundly limiting. A significant problem with this representation is that it does not visually communicate any aspect, or even the existence, of the quantum vacuum, let alone the quantum vacuum ground state, that is, the zero-point field. The standard model of cosmology representation of the universe is derived from general relativity. Unfortunately, the future of cosmology is not general relativity. The future of cosmology is the quantum vacuum, that is, the integration of general relativity with quantum mechanics. The most obvious integration point between these two disciplines is the quantum vacuum. It is important to note that, in the standard model of cosmology conceptualization shown, the diameter of the sphere denotes the size of the observable universe, that is, approximately 92 to 93 billion light-years. Illustrated on the right-hand side of the screen, is the quantum model of cosmology. The quantum model of cosmology is an equivalent representation of the standard model of cosmology, but also includes the quantum vacuum. The quantum model of cosmology is a sphere of Hubble radius, enveloping the quantum vacuum. Specifically, the quantum vacuum in its ground state, termed the zero-point field. The radius of the sphere changes with Hubble time, and the observable universe rests upon the surface of the sphere. This means that, in order to circumnavigate the observable universe, a traveler must move all the way around the sphere, returning to their starting position. By doing so, the traveler has moved approximately 92 to 93 billion light-years, which is equal to the diameter of the standard model of cosmology conceptualization on the left-hand side of the screen. In other words, the perimeter of the quantum model of cosmology equals the diameter of the standard model of cosmology. We shall exploit this relationship in order to derive some astonishing experimentally verified results, thus proving that the true age of the universe is the Hubble age. Let's now look at the math. The first thing we're going to do is look at the standard model of cosmology solution for cosmological age. Within the boxed region, you'll see equation 1. This is the general solution. When we set z equals 0, we get equation 2, which is just a simplified form of equation 1. Z is termed redshift, and setting it to 0 means that the amount of space-time stretching at your eye level is 0. As we look back across the universe, the stretching increases and so does the value of z. Hence, higher z means farther back in time, which means an older cosmological age. You can also see that equation 1 and 2 are equal from the calculated output of 13.8 billion years. The next thing we're going to do is select an alternative representation of general relativity. The reason we're doing this is because if we limit ourselves to general relativity only, and general relativity has produced an incorrect result, then we cannot catch the mistake. To catch a mistake, we need alternative forms of calculation in order to make comparisons, and consequently, validating both of them. Equation 3 is termed the refractive index, which comes from the polarizable vacuum model of gravity. Multiple forms of refractive index exist, but the form shown in equation 3 relates cosmological redshift to the refractive index. Typically, when applying the polarizable vacuum model of general relativity, an observer is outside a gravity well, looking down. However, in cosmology, the reverse is true. Think of it like this. Where is the center of the universe? Everywhere. Therefore, where is the center of mass of the universe? Everywhere. This means that an observer is always at the cosmological center of mass, and must always be at the bottom of a gravity well, looking up. This is what the form of refractive index shown by equation 3 does. It places an observer at the bottom of a gravity well, looking up. When we plug equation 3 into equation 1, we obtain equation 4. As we can see, the result from equation 4 equals the result from equation 1 and 2, as it should. Therefore, we have proven that the polarizable vacuum model of gravity is isomorphic to general relativity, that is, it's equivalent to general relativity. With this proven, we can move on to the next phase of the derivation. In phase 2, we'll utilize equation 5, which is a form of refractive index developed by Depp and Deciato, satisfying the Reissner-Nordstrom general relativity solutions. This is an explicitly gravitational form of refractive index, whereby an observer stands outside a gravity well, looking down. We'll utilize equation 5 to derive the dark energy refractive index. The dark energy refractive index denotes the refractive index of space-time, specifically and solely associated with dark energy. In other words, the dark energy refractive index is a measure of how much dark energy curves spacetime. The standard model of cosmology is incapable of such a calculation because it considers photons to be massless. The electrogravimagnetic construct considers the quantum vacuum to be an effervescent source of massive photons, and this is why we believe the standard model of cosmology calculation of cosmological age to be incorrect. We'll speak more about this later on, but for now, we'll return to the derivation. If an observer stands on the surface of the quantum model of cosmology sphere appearing on slide 2, looking across the universe, the most distant possible observation is given by equation 6. Equation 7 denotes the massive composition of the quantum vacuum. We can see that the dark energy parameter acts upon the volume of the quantum model of cosmology sphere, which in turn acts upon the critical cosmological density. Experimental observations have proven the space-time geometry of the universe to be flat. This means that its mass density must be very close to its critical density. If the universe is precisely and exactly flat, and the critical density exactly equal to its mass density, then the universe will stop expanding, but only after an infinite amount of time. Following the arrows on screen, and executing the required substitutions, we arrive at the dark energy refractive index equation. On the next slide, we will show you how this may be applied to correct the standard model of cosmology value of cosmological age, that is, proving that 13.8 billion years is the incorrect age. By applying the polarizable vacuum model of gravity time dilation equation, in terms of the dark energy refractive index, appearing here as equation 11, yields equation 12. As we can see, equation 12 is simply equation 2, multiplied by a missing term. The missing term is the dark energy refractive index. Equation 12 may be evaluated with particle data group 2022 inputs, to clearly show that cracks are starting to appear in the standard model of cosmology estimate of cosmological age. However, this evidence isn't completely convincing by itself. Can we do more? Yes, of course we can. Let's recall the present epoch cosmic microwave background radiation temperature equation derived in episode 11. We can utilize this equation to constrain the cosmological Hubble constant, that is, the power spectrum Hubble constant, to the cosmic microwave background radiation temperature. Once we've determined the cosmic microwave background radiation temperature constraint value of Hubble constant, we can recompute equation 12. Once again, we obtain a solution very similar to our initial output. Hence, another crack has appeared in the standard model of cosmology estimate of cosmological age. But also once again, can we do more? Yes, of course we can. In phase 4, let's propose an hypothesis. Let's hypothesize that the true value of cosmological age is equal to the Hubble age. This means that equation 12 may be simplified in accordance with equation 14. Once we do this, and evaluate for dark energy parameter, we obtain a value almost precisely equal to the particle data group 2022 value. This is an astonishing result and cannot be coincidental. This means that we have arrived at a solution where the power spectrum Hubble constant and the dark energy parameter are both constrained by the cosmic microwave background radiation temperature. Therefore, the true cosmological age can only be the Hubble age. Let's now pull everything together on the next slide. As everybody knows, the standard model of cosmology predicts that the age of the universe is 13.8 billion years. What is not generally appreciated is that cosmological age is a calculation, not a measurement. An answer of 13.8 billion years was calculated, it wasn't measured. The primary reason this mistake has not been captured is because the only tool available to the standard model of cosmology is general relativity. This means that, whatever general relativity says, cannot be challenged because no alternative exists. Imagine if all branches of science suffered the same limitation, we'd be in serious trouble. However, as you can see on screen, we have shown that the polarizable vacuum model of gravity yields an identical result on a like-for-like substitution basis. Equation 11 denotes the common link between general relativity and the polarizable vacuum model of gravity, with respect to dark energy. As far as the standard model of cosmology is concerned, photons are massless, so the value of refractive index is unity. However, within the electrogravity-magnetic construct, photons are massive and consequently, time is dilated during cosmological expansion. We need to remember that, as far as general relativity is concerned, virtual photons entering existence from the quantum vacuum during cosmological expansion are massless photons and therefore cannot modify the cosmological age calculation. Let's now summarize our adventure. Here is what we've learned. Number 1. Cosmological age is a calculation, not a measurement. Number 2. The standard model of cosmology use of z equals 0 introduces a fundamental flaw into their cosmological age calculation. Z equals 0 is an assigned value, not an assumed value. Assumed values may have basis in fact, an assigned value is simply allocated. Assigning a value of z equals 0 is only valid if photons are indeed massless. However, we have shown this to not be the case. Number 3. The true cosmological age equals the Hubble age. That is, 14.57 billion years. The standard model of cosmology value of 13.8 billion years is incorrect. And number 4, we have constrained cosmological age, the experimentally validated power spectrum Hubble constant, and the experimentally validated dark energy parameter to the cosmic microwave background radiation temperature. For viewers wishing to consult literature relevant to this episode, you may do so by accessing the links shown.